In a previous video, we were introduced to exponential functions and their graphs. In this video, we're going to look at applications of exponential functions. Specifically, we want to solve problems and applications involving exponential functions. Okay, let's recap what we know. Well, we know what an exponential function is. It is any function of the form y equals b to the x, where b is greater than or equal to 0 and not equal to 1, and x is any real number. As a reminder, the number b is called the base, and in an exponential function, the exponent is the variable. You may have studied power functions. In a power function, the base is the variable. In an exponential function, the exponent is the variable. All right, our first example, we'll solve a problem here. Set it up a little bit for you. We want to find the base of the function y equals b to the x if its graph passes through the point -2, 64. So we have a function, we have an equation, and we know a point that is on the graph. A point that is on the graph makes the equation true. So we can substitute x and y with this x and y and solve for b because this point is on the graph. It makes the equation true. So let's start off. We have our base equation, y equals b to the x. We know that -2, 64 makes it true. So we can substitute 64 in for y and -2 in for x. Now we have one equation with one unknown. It can be solved. Well, let's first remember that a negative in the exponent means the reciprocal, 1 over. So I'll write this b to the -2 as 1 over b squared. Okay? Now we need to get b squared out of the denominator. So if you'd like, I'll multiply both sides times b squared. Okay, so I'll have 64b squared is equal to 1. Well, that's a little nicer. Get rid of that fraction. Now I can solve for b squared by dividing both sides by 64. So b squared is equal to 1 over 64. And now I can find b by taking the square root of both sides. And so b is equal to plus or minus. Don't forget, you have two possibilities. The square root of 1 is 1. The square root of 64 is 8. So b is equal to positive or negative 1/8. However, let's recall, I'll look back up here at the things we know. Let's recall our b is our base, but b must be positive. Okay, our base is always positive. And so in this case, it cannot be negative 1/8. So b is equal to positive 1/8 because b is greater than 0. Okay, so this tells us that the equation here, the base of 1/8, will create an exponential function that passes through the point -2, 64. So here's our function, y equals, and I'll use parentheses, just makes it look a little bit nicer, 1/8 raised to the x power. Let's check it with Desmos. So give me a second to set this up and get into Desmos. Okay, as it loads up here for us. Okay, so let's take a look here. The equation, I'll put the equation, the function we have, the equation y is equal to, and I like to use parentheses just to make it, it just kind of clarifies it. So 1/8 raised to the x power. And here it is. Now let's recognize that our base is a proper fraction. And we know that when our base is between 0 and 1, the graph decreases from left to right. So as x increases, the graph is decreasing, the function is decreasing. And we want to see if negative 264 is on the graph. Well, negative 264 is going to be up in here somewhere. I had to do a little bit of I guess I zoomed out. So it's in here someplace. It's not a point that's on an axis, so it's not a key point. So we can go into here, number 2, and we can put the point in and see if it falls on that. So we'll put in negative 2, comma 64. And we can see, sure enough, right there it is. It's on the graph. If you want to click the label, it'll label that point right there for you. Negative 264 is on the graph. So we feel confident, we feel assured, I guess I should say, that the equation of the exponential function is y equals 1/8 to the x. All right, let's do another example here in which we're just going to use the graph to come up with the answer. So let me scroll down here a little bit and get my, okay, there we go. Okay, use a calculator. We're going to use a graph, use a graphing calculator to find the value or values for which x cubed is equal to 3 to the x. As a reminder, x cubed is a power function because the variable is in the base. 3 to the x is an exponential function because the variable is in the exponent. So we'll simply put in the left side, and we'll graph it, and we'll graph the right side, and then we will see where these two graphs intersect, because that will be the answer. Okay, so let's go back to Desmos. Okay, get myself again set up here. Alrighty. Okay, let's get out of these two, start again. So I have a y is equal to x cubed, x to the 3rd power. And there's your function there. We know if you've seen power functions before, the odd functions have this shape coming up from the left, crossing through the origin, and then going up to the right. Those are all your odd power functions. Now let's put in our exponential function. Y is equal to 3 to the x. And with our base of 3, which is greater than 1, we know that it increases as it goes from left to right. Now notice what Desmos did already. I've highlighted here is the second one, the exponential function. And Desmos has already, Desmos picks out key points for you. And key points include intercepts. Well, there's the intercept of the exponential function right here, which is 0, 1. And key points also include where they intersect. So in this case, it turns out that these two functions intersect. There are two values for x. They have two places that they are equivalent. One is a nice integer answer, 3, 27. The other one is looks like Desmos is probably giving us an approximation here to the thousandths place, but somewhere around 2.5 and 15 approximately is also where these two graphs intersect. So they intersect at two locations. And again, Desmos, if I highlighted the top one, it'll give me the intercept of the power function, and then again it'll give me the key points of where it intersects the other function. So there we have it. We have two answers: when x equals 3, and when x equals approximately, I would imagine, 2.478. Okay, so let's go back over to our notes, our paper here, and we came up with two answers. Okay, find the values for which this is true. Well, we have two, when x is equal to 3, and when x is equal to, I guess I should use approximately equal to. I'm not so sure that's an exact answer. and Desmos gave us 2.478. So graphs will give us answers to such things that we can't answer algebraically, or at least we haven't seen how to do that. Maybe you have in the past, but I have not done that yet. Okay, one more example. This one's going to be kind of have a real-life application using an exponential function. Okay, let's see here. A medical research lab is growing a virus for a vaccine that grows at a rate of 2.3% per hour. Okay, they started off with 500 units of the virus, and they're telling us here that the amount present after 2 hours, so at time equals 0 hours, they had 500 units. The amount present after t hours, 1, 2, 3, etc., is given by n, probably the number of the virus, is equal to 500 times 1.023 raised to the t, which is again hours, the time in hours. How many units of the virus are present after 2 days? Well, the first thing we want to recognize is that t is in hours, and we want to see how many are present after 2 days. Well, our equation requires hours. So we're going to need to specify that 2 days is equivalent to 48 hours, because we need t to be in hours. And now we can use our exponential function here. N is equal to 500 times 1.023 to the t. Well, we want to know after 48 hours, so we'll put in 48 in the exponent. And this is a calculation. So how much of the virus will there be after 48 hours? We'll do this math out, and you come up with 1,489.36. Probably rounded that to the hundredth. They called it units, so I'll call it units. So 1,489.36 units of the virus will be present after 2 days, which is the same as 48 hours. Well, there you have it. A little bit of work with applications of exponential functions.